So today let's try to somehow remove the resin from this high voltage module from the stun gun from the previous video. To be able to see the internal components of it and reverse engineer the schematic of it. I already reverse engineered the schematic of the rest of it, but this module is still a mystery. Can I somehow melt it or dissolve it in acetone or ethanol or a lacquer thinner? Let's basically put a drop of each on it to compare the effect of it on it. It doesn't seem to dissolve, or at least not very quickly, so let's put some samples of it in it and see a long-term effect. And let's try to bake this one. Can I melt it or soften it by baking it, by using a high temperature? So maybe let's try to bake it. Let's see what happens. Let's give it 150 degrees Celsius. And maybe let's give it a hot air. I'm trying to soften it by heat, but anyway, let's also try to dissolve it in one more chemical. In this drain cleaner, which is basically a sodium hydroxide. It comes in a powder or some kind of lumps. So let's put some here, add some water and put some sample of it in it. Let's add some water to dissolve it. I should have probably used the hot water to dissolve it faster, but anyway, there is a little bit left undissolved. Maybe I put too much in it. But anyway, let's try to put a sample of it in it, a sample of the resin, and see if it dissolves or not. So does a sodium hydroxide dissolve it? And of course, this is a nice picture. So it was baking for about an hour, which is probably too much, at 150 degrees Celsius, which is probably also a bit too much, but anyway, let's see the result. So here it is, and surprisingly the isolation on the wires is not even a molten match, or they kind of slightly stick together, but they are not molten. And it now feels kind of soft, kind of rubbery. It's definitely not hard like it was before. Before this, it was quite hard, like glass or porcelain. Now it's more like rubber. Can I remove pieces of it? Kind of. Well, now it's definitely a bit easier to remove than before. But unfortunately, it cools down and hardens again. So now it's about a week later and I wasn't at home, so I left the samples of the resin in the chemicals a bit longer than I planned. I planned to leave it in the chemicals for about 1 or 2 days, but I had to leave my home, so it was about 7 or 8 days. But now let's take a look at it. The lacquer thinner actually completely evaporated from it, but the acetone and ethanol are still there a little bit. So it seems that this lacquer thinner evaporates faster, and it was covered by this box to slow down the evaporation, but it's definitely not airtight. Now let's see the samples. Let's remove them using scissors, because this is my tool for absolutely everything, and this is the lacquer thinner, and it's kind of softened. It's like almost like a jelly or a rubber. It's definitely softened quite a lot. That's from the lacquer thinner, and it's quite rubbery. You can cut it using scissors easily. It's like rubber. And the one from the ethanol, on the other hand, is still hard. Well, it's slightly softened, but definitely not so much. It's like a very hard rubber or piece of plastic. And the one from acetone, let's do a scissor test, and it's actually even worse. It's even harder than from the ethanol. So the conclusion is that acetone doesn't soften it much. Ethanol is just a little bit better, but definitely the best one is a lacquer thinner. And here's the one in the drain cleaner. And the water actually evaporated from it and it formed crystals. And is it actually dissolved? It doesn't seem so. It's quite hard. I can't cut it using the scissors. I can just crack it, so it's still hard. So the lacquer thinner is definitely the winner. So the entire module goes into the lacquer thinner, of course. But of course this will take a lot of time, and let's put a sticky tape over it so it doesn't evaporate so much. And it seems like that just after a couple minutes, the rubber isolation on the wires soaks the thinner and it's getting bigger, it expands. But now let's leave it sitting. I probably have to wait for at least a couple days. After 1 day, it seems that the rubber isolation on the wires is falling apart and some small pieces come off from the resin, but the bigger pieces of it are still hard. Now it's 3 days and it looks like it's kind of dissolving and some pieces falling off, and unfortunately it evaporates, so I have to add some. Looks like it's getting softer and it's falling off near the transformer. Now it's 9 days and it seems to go slowly and small pieces are coming off, but the bigger ones are still quite hard. And it seems like it cracked the ferrite of the transformer because it's kind of shrinking or expanding as it's soaking in the thinner. So it seems to be kind of softened and some pieces may come off. Not sure if I damage it or not. Of course the ferrite core fell apart because it's expanding, not shrinking. It's definitely not easy to open. And the positive seems to come in and go to 2 different windings, or probably a center tap of a winding, because it's probably some self-oscillating circuitry with 1 transistor, and it seems to be TO220 package transistor, or the plastic version of the package basically. Some pieces of the resin are softened, but some pieces are still quite hard. It seems like the thinner actually softens it just to a certain depth. It can easily soften small pieces, but not a huge chunk of it. And the transformer basically falls apart, and I can see some primary, with probably also some auxiliary winding as a feedback winding, and the high voltage secondary is in the center of the transformer. They made the high voltage secondary and then they put the other windings over it basically. And here's the transistor, and here's some diode and a resistor, and of course its marking is dissolved now, and probably some high voltage capacitor here. And so let's peel the softened layer of the resin and put it back into the thinner. And of course I completely forgot about it, so now it's sitting in the thinner for about a month or even more. But I covered it using this and plus another layer of sticky tape, so the thinner didn't evaporate. It's still there. So now let's try to see the effect. Let's remove it from it using scissors, of course, and it seems to be kind of dissolving or softening at least a little bit. And if the thinner doesn't dissolve it, I can try to dissolve it in my fire extinguisher or get some better chemical for this. The thinner is probably not ideal. Now it's all kind of falling apart, and here's probably the secondary winding in the center of it with some thin wire and the center of the ferrite core. So here's the secondary, probably a very thin wire. And another piece of the broken secondary here, and the primary, and maybe some auxiliary winding for a self-oscillating circuitry. And there are actually 3 types of wire. The thinnest one for the secondary, some medium thickness one, probably for the auxiliary winding, and to basically make it oscillate, it's probably self-oscillating, and the thickest wire for the primary. It's completely falling apart, and here's the transistor with some diode on it connected to its emitter or source, depending on if it's a bipolar transistor or a MOSFET. And the thick wire, the primary, goes to its collector or drain. And the thinner wire, the auxiliary, goes to its gate or base. And also its emitter or source goes to the negative terminal. And here's a pair of resistors, probably a resistive divider, and the center of it goes to the other end of the auxiliary winding, and one end of it goes to the positive terminal, and also to the other end of the primary. And this one, I don't know, it's broken. And it seems like the big resistor broke from here, from the diode. And now let's try to measure the components and try to put those pieces together and draw the schematic of the primary side. So here's the schematic of the primary side of it, which is quite simple. I measured the resistors and the polarity of this diode, and I also measured this transistor, and it's not a MOSFET, it's a bipolar transistor, and it's NPN. And here's the auxiliary winding and the thick primary winding. And it's basically just a single transistor self-oscillating circuit. The transistor switches the primary, and there is a feedback, a positive feedback into the base of it to make it oscillate. When a voltage is connected to it, this resistor supplies a small current into the base of this transistor, and it partially turns on, and it connects some voltage to this winding in this polarity, to the primary basically. And also some voltage appears on the auxiliary winding, supplying even more current into the base of the transistor via this diode and this resistor. So the transistor turns fully on until the core saturates, or the current is too high in the primary and the transistor desaturates, and then the voltage on the auxiliary winding falls and it turns fully off. And then the voltage is the other way when it's off, and it supplies a negative voltage to the base, keeping the transistor fully off, until the energy runs out in the core of the transformer, and then it repeats. When the energy in the core of the transformer runs out, the negative voltage disappears from the auxiliary, and so the cycle can repeat, because it no longer keeps the transistor off. And of course the reason for this diode is that if there wasn't this diode, it would be a resistive divider, but because this resistor is about 100 times less resistance than this one, there would be about 1% of the input voltage here, and this wouldn't be enough to turn the transistor on. The diode is here, so the current can go in this direction into the base of the transistor, but without the diode, the resistor would basically pull the voltage down here. And now let's take a look at the secondary side. Obviously the transformer has to have some secondary, and this secondary has to go into some circuitry, probably a voltage multiplier with some capacitors and diodes, and maybe some discharging resistor, a high voltage resistor to discharge the capacitors. And I'm removing the resin, and it's quite weird because some parts of it are quite soft and rubbery, but some other parts of it are still quite hard, like a stone. And there are some blue high voltage capacitors, but the blue material on top of it is falling apart, and just the internals of the capacitors remain. It basically looks like a multiplier. It has 4 terminals. 2 terminals coming from the secondary of the transformer, and 2 terminals to the output electrodes, which give you a shock. And this capacitor falls apart, and some other capacitor comes out here, and here you can see the internals of the first capacitor. And this capacitor definitely seems to be a bigger one than this one. The big capacitor is 1.2 nanofarads, and the small ones are about 100 picofarads. And of course there is some capacitance of the probes, so it shows about 120, but when I put the probes a little bit away from the capacitor, it still shows about 19 or 20, so it has to be subtracted. And now it's completely deconstructed, and you can see the internals of the small capacitors, 2 of them, and 1 big capacitor, and 3 diodes in series, and there is also a high voltage resistor, which was in parallel to this high voltage big capacitor. And the capacitors have no marking or no visible marking, but at least I was able to measure them. And here's the full schematic of it, and it's basically a 3-stage multiplier. And basically when the polarity of the secondary is like this, it charges this capacitor via this diode to this polarity to one peak voltage of the transformer, and when the polarity is the other way, then the voltage of the secondary adds to the voltage of this capacitor, so it doubles the voltage, and via this diode it charges this capacitor to double the voltage, basically 2 peak voltages of the secondary. And then the polarity is like this again, and the voltage of this capacitor adds to the voltage of the secondary, and you get triple voltage, and this charges this capacitor via this diode like this, and it charges it to the triple voltage. And so this big capacitor is charged to 3 times the peak voltage on this secondary, or to be more accurate, it's actually twice the peak voltage in this polarity, plus once the peak voltage in this polarity. And it's a single transistor switching, so it switches the primary in just one polarity, and so the voltage just inductively overshoots into the other polarity. And the peak voltage can be different in each polarity. And you also have some discharging resistor to discharge the capacitor. So when you release the switch of the stun gun, you no longer can get an electric shock from those electrodes. And of course this high voltage resistor is not measurable by normal multimeter. Usually multimeters go up to about 20 or 30 mega ohms, but I guess this could be about 100 mega ohms or even 1 giga ohm. It's basically a resistive track on a ceramic plate, and of course it relies on the resin. It has to be in resin, otherwise it would probably arc over. So the resistance of the resistor was probably in this ballpark, and the spark was about 10 millimeters, which could be about 10 kilovolts, and so the dissipation of a 1 giga ohm resistor would be 0.1 watts. If it was 100 mega ohms, it would be 1 watt. So that's the internals of the high voltage module in resin. And of course the rest of the stun gun was shown and reverse engineered in one of my previous videos. I will put a link to it into the description. And here is the rest of the stun gun. So this is Diagonal Wild, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support. And of course my patrons get early videos, at least 1 day earlier. And I also plan to show my solid-state Tesla coil running at DC voltage, and I also plan to take a look at this interesting donated charger for 2 lithium-ion batteries with this USB cable and some other switching power supplies, of course.